September 7th, 2025. A telescope in Hawaii swivels automatically toward a coordinate in the southern sky. The machine doesn't know what it's looking for. It simply obeys its programming. Scan, capture, catalog. The Atlas survey system has done this millions of times. Most nights it finds asteroids, sometimes comets, occasionally space debris reflecting sunlight back toward Earth. Tonight it finds something else. The object appears as a smudge of light against the background stars. Faint, moving. The automated software flags it immediately, not because it's unusual, but because it's moving in a way that suggests it doesn't belong to our solar system. The velocity is wrong. The trajectory is wrong. Within hours, the data transmits to the Minor Planet Center in Cambridge, Massachusetts. By morning, 3 other observatories confirm the sighting. They name it 3I Atlas, the third known interstellar object ever detected. But naming something doesn't mean understanding it. The first, interstellar visitor, 1I Oumuamua, arrived in 2017 like a postcard from another star system. It was strange, cigar-shaped, tumbling, accelerating in ways that didn't match any known physics of comets or asteroids. Scientists debated for years. Some said it was a comet outgassing asymmetrically. Others proposed more exotic explanations. The argument never fully resolved. The second visitor, 2I Borisov, showed up in 2019. It behaved exactly like a comet should. Astronomers were almost relieved. The universe, it seemed, could still play by familiar rules. 3I Atlas is different. Within the first week of observation, the Hubble Space Telescope locks onto it. The object is roughly 3 kilometers across, small enough to escape detection until it wandered relatively close, large enough to capture in detail once located. Its surface reflects light in a way that suggests ice mixed with darker material, possibly carbon compounds or silicates. This fits the profile of a comet, a dirty snowball, from the deep freeze of interstellar space, now warming as it approaches our sun. But then the color changes. On September 12th, astronomers at the Very Large Telescope in Chile noticed something unusual in the spectroscopic data. The object's light signature shifts, not gradually as would happen with changing solar illumination, but abruptly. One night it reflects light in the blue-white range. The next night, it has taken on a warmer reddish hue. Comets don't do this. Comets can change brightness as they outgas, releasing jets of vapor that catch sunlight, but their color remains relatively stable. The color of a comet is determined by its composition: water ice, frozen carbon dioxide, methane, ammonia. These materials don't suddenly transform from one substance to another, yet the data doesn't lie. The shift happens again on September 19th, blue to red. Then, 2 days later, red back to blue. The pattern is irregular, but unmistakable. Something about the object's surface or surrounding cloud of gas and dust is changing in real time. Avi Loeb, a theoretical astrophysicist at Harvard, is among the first to comment publicly. He's careful with his language, but the implications are clear. When an object exhibits properties that don't fit our models, we have 2 choices. We can assume we don't understand the physics well enough, or we can consider that the object itself might not be what we think it is. The scientific community responds with predictable caution. Comets are complex. Outgassing can be asymmetric. Surface materials can sublimate at different rates depending on solar heating. Perhaps the color shift is simply a poorly understood natural phenomenon, a quirk of chemistry and thermodynamics we haven't fully mapped yet. But then the object begins to eject material. On September 24th, instruments detect a plume of gas streaming from 3I Atlas. This is expected. Comets shed material as they heat up, but the composition of the plume is wrong. Spectrometers identify hydrogen cyanide, a common component of comets, but also nickel vapor, and not just trace amounts. The concentration of nickel is orders of magnitude higher than anything observed in natural cometary outgassing. Nickel is a metal. It doesn't sublimate easily. To release nickel vapor, you need temperatures exceeding 2,900 degrees Celsius. The surface of 3I Atlas, even at its closest approach to the Sun, shouldn't reach anywhere near that temperature. Yet the instruments don't. Malfunction. The readings repeat across multiple observatories. The nickel is real. Iron, which normally accompanies nickel in cosmic debris, is conspicuously absent. This is the first contradiction. Comets are ancient, formed from the primordial material of stellar nurseries. In those environments, nickel and iron are almost always bound together. They're siblings in the periodic table, formed in the same supernova explosions, condensed together in the same dust clouds. Finding one without the other is like finding a river with no water. Technically possible, but so improbable it demands explanation. No one has one. By the end of September, 3I Atlas has become the most observed object in the solar system aside from the Sun itself. Telescopes on every continent track it. Space-based observatories adjust their schedules to prioritize it. Data pours in faster than it can be analyzed. And with each new data set, the object becomes less like a comet and more like a riddle written in the language of physics. The first major news outlets pick up the story on October 1st. Headlines are cautious but suggestive. Interstellar object behaves oddly. Astronomers puzzled by new visitor. The stories mention the color shifts and the nickel anomaly, but they frame everything as an unsolved scientific puzzle. No one uses the word artificial in print. Not yet. But in private, conversations are different. Emails circulate among research groups. Theoretical papers are drafted, then deleted. Conference calls stretch past midnight as astronomers compare notes and check each other's math. The object is moving on a hyperbolic trajectory, meaning it's definitely from outside the solar system, not just a long-period comet returning after millennia. Its speed and path suggest it originated from somewhere in the direction of the constellation Lyra, though tracing its exact origin is impossible. Interstellar space is vast. Objects drift for millions of years, their birthplaces long, forgotten. Still, the object is here now, and it's behaving in ways that resist easy categorization. On October 7th, a team at Penn State publishes a preliminary analysis. They model the outgassing rate, the speed at which 3I Atlas is shedding material, and estimate it's losing approximately 150 kilograms per second. This is substantial but not extreme for a comet of its size. However, the mass loss should produce a measurable change in the object's trajectory. Comets that outgas create a tiny rocket effect. The escaping vapor pushes against the nucleus, altering its path slightly. 3I Atlas doesn't deviate. Its trajectory remains perfectly consistent with gravitational mechanics alone. It's as if the object is losing mass without experiencing any corresponding thrust. Newton's third law, every action has an equal and opposite reaction, seems negotiable here. The paper is peer-reviewed and published within 2 weeks, an almost unprecedented speed in academic astronomy. The conclusion is carefully worded. Further observation is required to determine whether current cometary models adequately describe the behavior of 3I Atlas. Translation: we don't know what's happening. The object continues toward the Sun. Its path will take it inside the orbit of Mars, then swing around our star in a tight parabolic arc before racing back out into the dark. Closest approach is calculated for mid-December. Astronomers prepare for the peak observing window, the brief span when the object will be brightest, closest, most revealing. But something else happens first. On October 29th, the Sun positions itself directly between Earth and 3I Atlas, a solar eclipse from the perspective of the object. For human observers, it's simply an alignment. For the object, if it has any awareness at all, it's a moment of shadow. The Sun's light, which has been heating its surface for weeks, vanishes. Temperatures plummet. The outgassing should slow or stop. Instead, the object brightens. Multiple observatories detect the change simultaneously. The light curve, the graph showing brightness over time, spikes upward just as the eclipse begins. Then, as the Sun's direct light returns, the brightness drops back to expected levels. The event lasts 19 minutes. 19 minutes during which 3I Atlas behaves exactly opposite to how any natural body should. Comets don't brighten in shadow. They dim. They need solar energy to drive the sublimation of ice, remove the sun, and the process slows. This is basic thermodynamics, confirmed by every comet ever observed. Except this one. The data is rechecked. Observatories compare timestamps. Instruments are calibrated. The result stands. During the eclipse, 3I Atlas emitted more light than it should have. Not by a little, by a factor of 12. No press releases are issued, no official statements are made. But within the astronomy community, the silence is louder than any announcement. Because if the object isn't powered by the sun, if it has an internal energy source capable of producing light independent of solar heating, then the question stops being what kind of comet is this and starts being something much harder to answer. Late on the night of October 29th, an astronomer in Chile sends a message to a colleague in California. The message is brief, only 3 sentences long. It's not recorded in any official log, but multiple people who saw it later recall the same phrasing. The object knows when it's being watched, or it knows when it's not. Either way, we need to be very careful about what we say next. The next morning, headlines begin to shift, and somewhere, 150 million kilometers away, 3I Atlas continues its silent approach. What if the first proof of intelligent life wasn't life at all? To understand what makes 3I Atlas strange, you first need to understand what makes comets normal. Comets are ancient. They formed over 4 billion years ago in the cold outer regions of star systems, where temperatures hover just above absolute zero. Water freezes into ice. Gases like methane and ammonia solidify into frost. Dust grains, the microscopic remnants of dead stars, stick together in the darkness. Over millions of years, these grains accumulate into loose, porous structures, cosmic snowballs held together by gravity so weak you could escape it with a running jump. Most comets never leave their birthplaces. They orbit in distant, frozen reservoirs, the Kuiper Belt beyond Neptune, or the even more remote Oort cloud, a spherical shell of icy debris stretching halfway to the nearest star. They wait. Some will wait forever, others get nudged. A passing star, a gravitational ripple from a nearby planetary system, even the slow tidal pull of the galaxy itself, any of these can disturb a comet's orbit. The object begins to fall inward, toward the star it's been circling for eons. As it descends, sunlight warms its surface. Ice sublimates, turns directly from solid to gas, and escapes into space. This creates the glowing cloud, or coma, that makes comets visible. The solar wind, a stream of charged particles flowing outward from the star, pushes the gas into a tail that always points away from the sun. This is Comet 101. Predictable, repeatable, understood. 3I Atlas doesn't follow the script. By early November, the object's mass loss rate is precisely measured at 150 kilograms per second. It's shedding the equivalent of a small car every 7 seconds. Over the course of a day, that's nearly 13 million kilograms, 13,000 metric tons of material streaming away into space. This should matter. It should change things. When a comet loses mass asymmetrically, and all comets do, because the sun heats one side more than the other, the escaping gas acts like a thruster. Imagine standing on ice and throwing a heavy ball. You'd slide backward. The same principle applies to comets. The venting gas pushes the nucleus in the opposite direction. Astronomers call this non-gravitational acceleration. It's tiny but measurable. For a comet losing 150 kilograms per second, the expected acceleration is roughly 0.0002 meters per second squared. That's minuscule, about 2 million times weaker than Earth's gravity, but over weeks and months it adds up. The comet's orbit should drift. Its trajectory should deviate from the pure gravitational path predicted by Newton's laws. 3I Atlas's trajectory doesn't deviate. Orbital mechanics are precise. Astronomers track objects using repeated observations, plotting their positions against the stars. With enough data points, you can calculate an orbit so accurate you can predict the object's location years in advance. Software does this automatically now, running thousands of calculations per second, comparing observed positions to predicted ones. For 3i Atlas, the numbers line up perfectly, but only if you ignore the outgassing. Jason Wright, an astrophysicist at Penn State, runs the calculations independently. He models the object as a standard. Comet inputs the observed mass loss rate and generates a predicted trajectory. Then he compares it to the actual trajectory measured by observatories. They don't match. The discrepancy is small at first, milliarc seconds of difference, the angular width of a human hair seen from a kilometer away. But the error compounds. By mid-November, the model predicts 3i Atlas should be 14,000 kilometers away from where it actually is. That's not a rounding error, that's a fundamental mismatch between observation and theory. Wright publishes a short paper on November 9th. The title is deliberately bland: Orbital Dynamics of 3i Atlas Preliminary Analysis. The conclusion is anything but bland. In careful academic language, it states, the observed trajectory is inconsistent with standard non-gravitational forces acting on a body with the measured outgassing rate. Either the mass loss is not producing thrust, or an additional force is acting on the object to precisely cancel the expected acceleration. Both possibilities are troubling. If the outgassing isn't producing thrust, then the gas is being released symmetrically, evenly in all directions, with no net push in any particular direction. But comets don't work that way. Comets tumble. They rotate irregularly. Their surfaces are uneven, covered with cliffs and craters and patches of varying composition. The sun heats them unevenly. Symmetrical outgassing would require a perfectly spherical object rotating at exactly the right speed, with its surface composition uniform down to microscopic scales. That's theoretically possible. It's also astronomically improbable. The second possibility is worse. An additional force is acting on the object. Not gravity, not solar radiation pressure, something else. Something strong enough to counteract the rocket effect of 150 kilograms per second streaming into space. If such a force exists, it's not in any physics textbook. The math doesn't lie. It also doesn't care about what seems reasonable. A small research group at the European Southern Observatory runs a different test. Instead of modeling the trajectory forward, they run it backward. They take the current position and velocity of 3i Atlas and calculate where it came from. Interstellar objects take millions of years to cross the gulf between stars. Trace the path far enough back, and you should arrive at the object's home system, the star it once orbited before some cosmic event flung it into the void. The calculation produces a strange result. 3i Atlas's trajectory, when traced backward, doesn't point cleanly to any nearby star. It originates from a diffuse region in the direction of Lyra, but the exact source is ambiguous. This isn't unusual by itself. Interstellar space is vast, and objects drift unpredictably over millions of years. But the uncertainty range is larger than expected. It's as if the object's past is deliberately blurred. One researcher describes it as trying to trace a river back to a spring, only to find the river splits into 100 tiny streams that vanish into the ground. By November 15th, a quiet tension settles over the astronomical community. Papers continue to publish, observations continue, press releases remain carefully worded. But in private communications, in late-night Zoom calls between collaborators, the language shifts. People stop saying comet without qualification. They start using terms like the object or the anomaly. No one wants to be the first to say what they're thinking. The Hubble Space Telescope captures a new image on November 18th. The resolution is high enough to resolve surface features, faint streaks and patches suggesting uneven composition. The image is enhanced, processed, analyzed pixel by pixel. Nothing looks artificial. Nothing looks engineered. It looks like a rock tumbling through space, illuminated by distant sunlight. But rocks don't lose mass without consequence. A journalist reaches out to Avi Loeb for comment. The resulting interview, published on November 20th, is measured but pointed. Loeb doesn't use the word artificial. He doesn't need to. We should follow the evidence wherever it leads, he says. If an object behaves in ways that natural models can't explain, then we need to consider a broader range of possibilities. Science progresses by confronting anomalies, not by explaining them away. The article generates 40,000 comments within 6 hours. Most are dismissive. It's just a comet. We don't understand everything yet. Loeb is trying to sell books. A smaller fraction is unsettled. What if he's right? Why isn't NASA saying more? This feels like Oumuamua all over again. A few are angry. Stop scaring people. This is irresponsible. Scientists should know better. The object indifferent to all of this continues inward. On November 22nd, the mass loss rate increases. Instruments now measure 180 kilograms per second, a 20% jump in less than 2 weeks. The outgassing intensifies as the object approaches the sun, which is expected. What isn't expected is that the trajectory still doesn't change. The acceleration that should result from 180 kilograms per second of thrust is even larger now, yet the orbit remains stubbornly Newtonian, pure gravity, no thrust, no deviation. A graduate student at Caltech runs a simulation. She models 3I Atlas as a sphere with active vents distributed across its surface. She tries random distributions, jets on one side, clustered. At the poles, scattered evenly. Then she tries symmetric distributions, carefully balanced to cancel out all thrust. The simulation runs for 6 hours. The result? To achieve perfect cancellation with an asymmetrically heated object, the vents would need to adjust their output in real time, responding dynamically to changing solar illumination. Not by a little, by fractions of a percent, recalibrated every few minutes. She saves the simulation file. She doesn't publish it. The implications are too uncomfortable, because real-time adjustment requires feedback. Feedback requires sensing. Sensing requires something that can detect changes in orientation, temperature, and solar flux, and respond accordingly. In engineering, that something is called a control system. By the end of November, orbital tracking stations around the world are monitoring 3I Atlas continuously. The object is now bright enough to be visible in large amateur telescopes. Dozens of independent observers log positions every night. The data feeds into a public database managed by the Minor Planet Center. Anyone with the right software can download the positions and run their own analysis. A high school physics teacher in Colorado does exactly that. He's not an expert, he's just curious. He plots the data, fits a trajectory, checks the residuals, the tiny differences between predicted and observed positions. The residuals should be random, scattered equally above and below the predicted line. Noise. They aren't. The deviations form a pattern, subtle but present. The object isn't just failing to accelerate from outgassing, it's moving as if guided, making tiny corrections that keep its path almost unnaturally smooth. He emails his analysis to JPL, NASA's Jet Propulsion Laboratory. He doesn't expect a response. He gets one anyway, 3 days later. It's brief. Thank you for your submission. Your analysis has been noted. No confirmation, no denial, just acknowledgement. The teacher posts his findings on an astronomy forum. Within hours, 3 other amateurs confirm the pattern using independent datasets. A professional astronomer at the University of Arizona sees the thread and runs her own analysis. She doesn't post the result publicly. She sends it directly to colleagues. The message is 2 sentences. The pattern is real. I don't know what it means. December arrives. The object is now 120 million kilometers from the Sun, closer than Earth, approaching the inner solar system where planets orbit in warm, stable paths. Ground-based telescopes track it nightly. Space telescopes pivot to follow it. The James Webb Space Telescope, the most powerful observatory ever built, locks onto 3I Atlas for a 14-hour observation run. The resulting data is embargoed, not published, not released, kept internal, but leaks happen. On December 3rd, an anonymous post appears on an astronomy subreddit. No credentials, no affiliation, just a short block of text. JWST detected infrared emissions from 3I Atlas inconsistent with blackbody radiation. Temperature gradient suggests internal heat source. Distribution is non-random. Data is under review. The post is deleted within an hour. Screenshots circulate anyway. NASA issues no comment. The object is now 17 days from its closest approach to the Sun. 17 days from the moment when it will be brightest, hottest, most exposed. 17 days from the point when every telescope on Earth and in orbit will be watching, recording, measuring. 17 days from when it will vanish behind the Sun and disappear from view for 51 days. The countdown begins. Nickel doesn't belong in comets. Not like this. To understand why, you need to go back 4.6 billion years to the birth of the solar system itself. In the beginning there was a cloud, a vast rotating disk of gas and dust collapsing under its own gravity. At the center, temperatures soared as matter compressed, eventually igniting nuclear fusion. The Sun was born. Farther out, where temperatures were cooler, leftover material began to clump. Rocky planets formed close to the Sun, where heat had vaporized lighter elements like hydrogen and helium. Gas giants formed farther out, where ice could survive and gravity could accumulate vast atmospheres. And beyond that, in the frozen dark, comets formed, icy bodies composed of whatever molecules could condense in the deep cold. The chemistry was simple. Water dominated. Carbon dioxide froze into dry ice. Methane, ammonia, and nitrogen formed icy crusts. Dust grains, tiny fragments of minerals, mixed throughout. And yes, metals were present. Iron, magnesium, silicon, nickel. But metals in comets don't exist as pure elements. They're locked inside minerals, bound into crystals like olivine and pyroxene, stable compounds that don't break apart without extreme heat. To release nickel vapor, you'd need to vaporize the minerals entirely. That requires temperatures exceeding 2,900 degrees Celsius. The surface of 3I Atlas, even at its closest approach to the Sun, shouldn't exceed 400 degrees Celsius, yet the spectrometers don't lie. On December 5th, the Very Large Telescope in Chile captures a high-resolution spectrum of the gas streaming from 3I Atlas. Spectroscopy is the art of splitting light into its component colors, its wavelengths, and reading the chemical fingerprints embedded within. Every element absorbs and emits light at specific wavelengths, unique as a barcode. Hydrogen has its signature. Oxygen has another. Nickel has its own. The spectrum shows hydrogen cyanide as expected. It shows water vapor, carbon monoxide, ammonia, standard cometary volatiles. And it shows nickel, not trace amounts, not faint hints buried in noise, strong, unmistakable emission lines, glowing bright in the ultraviolet. The concentration is approximately 3% of the total outgassing by mass. That means for every 100 kilograms of gas escaping 3I Atlas, 3 kilograms are nickel. For context, the most metal-rich meteorites found on Earth, chunks of shattered asteroids that survived atmospheric entry, contain nickel at concentrations around 5% to 10%. But meteorites are solid, dense, formed in the molten cores of planetesimals where metals settled and concentrated. Comets are the opposite, fluffy, low density, formed in cold environments where metals stayed locked in minerals. A comet with 3% nickel in its outgassing would need to be built differently from anything we've ever seen. Worse, iron is absent. Iron and nickel are siblings. They form together in the same stellar furnaces, bonded in the same minerals, locked into the same crystals. In every meteorite, every asteroid, every planetary core, nickel and iron appear together in a predictable ratio, roughly 1 nickel atom for every 10 iron atoms. Nature doesn't separate them easily. Yet, 3I Atlas is expelling nickel without iron. The spectroscopy is checked and rechecked. Different instruments, different observatories, same result. The iron. Lines are there, barely, at concentrations 100 times lower than they should be if nickel is present. It's as if someone filtered the elements, extracted one, left the other behind. No natural process does this, not stellar winds, not supernova shockwaves, not collisions, not radiation pressure. Iron and nickel are too chemically similar, their atomic masses too close. If a process can vaporize nickel, it will vaporize iron. If it can eject nickel from a surface, it will eject iron. Unless the process isn't natural. A team at MIT runs thermodynamic models. They simulate a comet with a nickel-rich core, heating unevenly under solar radiation. They try surfaces with varying compositions, rotation rates, volatile distributions. They model sublimation, outgassing, dust entrainment. They run 10,000 iterations. None produce the observed nickel-to-iron ratio. The closest they can get requires a comet with a pure nickel core surrounded by a shell of ice, a structure that would never form, naturally. Even then, the model only works if the ice sublimates in an impossibly perfect pattern, exposing the core evenly while somehow suppressing iron emissions. The lead researcher writes in his notes, "We're either missing fundamental physics or the object is made to do this." He doesn't publish the note, but he doesn't delete it either. On December 7th, a new anomaly emerges. The hydrogen cyanide emissions, the poison gas streaming from 3I Atlas, begin to pulse. Cyanide is common in comets. It forms when carbon, nitrogen, and hydrogen combine in the cold of space. When sunlight heats a comet, cyanide sublimates and escapes. The rate depends on temperature, which varies smoothly as the comet rotates and moves along its orbit. The emissions should be steady or at least gradually changing. 3I Atlas's cyanide output oscillates. Every 11.7 hours, the emission rate spikes, doubling over the span of 20 minutes, then drops back to baseline. The period is precise. Instruments at the ET, European Southern Observatory, track it for 3 full cycles. The timing is consistent down to the minute. 11.7 hours is a rotation period. That's the obvious explanation. The object is spinning, and as it rotates, a particularly active region faces the sun, releasing a burst of cyanide before rotating out of view. Many comets do something similar, though usually less dramatic. But there's a problem. If the cyanide pulse is caused by rotation, then the overall brightness of the object should also pulse with the same period. As the active region rotates into sunlight, it should brighten. As it rotates away, it should dim. The two signals, cyanide emission and visible brightness, should be synchronized. They aren't. The brightness of 3I Atlas varies, but on a different period, roughly 9.3 hours. The two cycles drift in and out of phase. Sometimes the cyanide pulse coincides with peak brightness. Other times, the brightness peaks when cyanide emissions are at their lowest. 2 rotation periods, same object. That's not possible unless the object has 2 distinct components rotating independently. A nucleus and a separate shell, perhaps, decoupled by some mechanism. Or 2 objects orbiting each other so closely they appear as one. Both scenarios are exotic. Neither has ever been confirmed in a comet. A researcher at Caltech proposes a third option in an internal memo. What if it's not rotating? What if the pulses are controlled? The memo doesn't elaborate. It doesn't need to. By December 10th, the object is 95 million kilometers from the Sun. Ground-based observations are becoming difficult, not because of distance, but because 3I Atlas is approaching the Sun's glare. Soon it will be visible only in daytime, washed out by the brilliance of our star. Space telescopes become critical. Hubble, JWST, and ESA's Solar Orbiter adjust schedules to maintain coverage. The mass loss rate continues to climb. By December 12th, instruments measure 210 kilograms per second. The object is now shedding 18 million kilograms per day, 18,000 metric tons. Over the past 3 months, it has lost an estimated 1.5 billion kilograms of material. This should be catastrophic. Comets that lose mass this quickly often disintegrate, breaking apart under thermal stress or tidal forces. 3I Atlas shows no sign of fragmentation. Its brightness remains steady. Its shape, as resolved by Hubble, is unchanged. It's as if the object has mass to spare. An astronomer at the University of Hawaii estimates the original mass of 3I Atlas based on its size and assumed density. For a 3-kilometer comet with typical cometary composition, the total mass should be around 30 to 50 billion kilograms. If it's been outgassing at the current rate since it first entered the inner solar system in August, it should have lost roughly 3% of its total mass by now. That's significant, but survivable. Comets can handle it. But here's the problem. The object hasn't been outgassing since August. It started outgassing when it was first detected in September, when it was already much closer to the Sun than most comets begin to outgas. The timing suggests it was dormant during the early approach, then activated suddenly. Why would a comet wait? Natural comets begin outgassing at predictable distances from the Sun, determined by the sublimation temperature of ice. Water ice starts to sublimate around 3 astronomical units, roughly the distance of the asteroid belt. Carbon dioxide begins earlier, around 5 AU. These are fixed thresholds governed by physics. 3I Atlas was inactive until it crossed inside 2.5 AU, then it turned on, all at once, as if it had decided to. A graduate student at UCLA is analyzing the color shifts, the blue to red transitions observed in September and October. She's trying to correlate the color changes with other observables: brightness, outgassing rate, solar distance. The data is messy, the transitions are irregular. But she notices something strange in the timestamps. The color shifts always occur at night, not the object's night, Earth's night. Every recorded color change happened when the object was being observed by telescopes in darkness, not during daytime observations from space-based platforms. It's probably coincidence. Daylight observations are harder, less frequent. Ground-based telescopes dominate the dataset, and they only work at night. The pattern could be an artifact of observing bias. She runs a statistical test anyway. If the color shifts are random, they should be equally likely during day and night observations once you account for the number of observations in each category. They aren't. The probability that the pattern is coincidental is 0.6%. She stares at the number for a long time, then she closes the file and doesn't mention it to her advisor. December 15th. The object is now 80 million kilometers from the Sun, inside the orbit of Venus. 4 days remain until closest approach. The observing window is narrowing. The Sun's glare is overwhelming ground-based instruments. Only space telescopes can maintain a clear view. And then, quietly, without announcement, NASA begins to reposition assets. The high-rise camera aboard the Mars Reconnaissance Orbiter, a high-resolution imager designed to photograph the Martian surface, pivots away from the planet. It points toward empty space, toward a coordinate along 3I Atlas's projected path. The camera locks on and begins a 72-hour continuous observation sequence. High-rise can resolve features as small as 30 centimeters from Martian orbit. Pointed at 3I Atlas from a distance of 200 million kilometers, its resolution is much coarser, but still capable of detecting structural details no Earth-based telescope can match. The data is classified as embargoed pending review. No explanation is given for why a Mars orbiter is being used to study an interstellar object. No press release announces the observation, but tracking logs are public. Amateur astronomers notice. Questions are asked. NASA's response: HiRISE occasionally observes non-Martian targets for calibration and extended mission objectives. The answer is technically true. It's also evasive. On December 16th, the Hubble Space Telescope captures its final pre-perihelion image of 3I Atlas. The object is now visibly surrounded by a coma, a glowing cloud of gas and dust extending 50,000 kilometers in every direction. The tail, pushed by solar wind, stretches behind it like a banner. It looks like a comet. Every visual cue suggests a comet, but the data beneath the image tells a different story. The dust-to-gas ratio, the relative amount of solid particles versus vapor in the coma, is wrong. Comets typically eject dust and gas in roughly equal proportions by mass. 3I Atlas is releasing almost pure gas. The dust fraction is less than 5%. Dust is heavy. It requires more energy to lift off the surface. A comet with weak gravity, like 3I Atlas, should have trouble retaining large dust grains, but it should still release plenty of small ones. The absence of dust suggests the surface is unusually smooth, or the outgassing is unusually energetic, or the object is selectively releasing volatiles while keeping solid material bound to its surface. No natural mechanism explains selective retention of dust while simultaneously venting massive amounts of gas. A planetary scientist at the University of Arizona runs a comparative analysis. She compiles dust-to-gas ratios from every well-studied comet in history: Halley-Hale-Bopp 67P Churyumov-Gerasimenko, Lovejoy-Ison. The ratios cluster between 0.3 and 3.0, meaning for every kilogram of gas, comets release between 300 grams and 3 kilograms of dust. 3I Atlas is releasing 50 grams of dust per kilogram of gas, 20 times less than the cleanest comet on record. She writes in her analysis, "The coma composition suggests either an object with an extraordinarily pure volatile reservoir or a mechanism that preferentially vents gas while constraining particulate ejection. Both scenarios are unprecedented in cometary science. The word mechanism is doing a lot of work in that sentence." December 17th. The object crosses inside the orbit of Mercury. Temperature on the sunlit side now exceeds 350 degrees Celsius. The outgassing rate peaks at 240 kilograms per second. The coma brightens. The tail extends. Every signature suggests a comet in distress, shedding material rapidly as it approaches the point of maximum solar heating. Except the object isn't in distress. Its trajectory remains stable. Its rotation, whatever its actual period is, shows no signs of the wobbling or precession that stressed comets typically exhibit. The nucleus, as imaged by Hubble, is intact. It's shedding mass like a dying comet, but behaving like one in perfect health. At 11 p.m. Universal Time on December 17th, the European Space Agency's solar orbiter captures a sequence of images in extreme ultraviolet light. This wavelength reveals the hottest, most energetic regions of the object's coma, the zones where solar radiation ionizes gas molecules, stripping away electrons and creating glowing plasma. The plasma is structured. Most comets produce diffuse, chaotic plasma clouds. Streams and filaments form randomly as solar wind interacts with outgassing. The patterns shift and dissolve within minutes. They're turbulent, like smoke in wind. The plasma around 3I Atlas is different. The ultraviolet images show radial streamers, straight, lines of ionized gas extending outward from the nucleus in a symmetrical pattern. 6 streamers, evenly spaced around the object's equator. Each one is approximately 8,000 kilometers long. They don't waver. They don't dissolve. For 3 hours, the streamers maintain their structure. Then, as the object rotates or as something changes, they vanish. The plasma cloud returns to normal diffuse chaos for 20 minutes. Then the streamers reappear, rotated 60 degrees from their previous orientation. Chidisa. Pattern repeats 4 times before the object rotates out of solar orbiter's field of view. A plasma physicist at Imperial College London sees the images. She spent 15 years studying solar wind interactions with comets. She's seen every kind of plasma structure nature can produce. Streamers, jets, turbulent cells, bull shocks. She's never seen symmetric radial structures that persist for hours. Magnetic fields, she says, in a hastily convened video call with ESA colleagues. Those streamers are following magnetic field lines. The object must have an internal magnetic field strong enough to channel plasma flow. One of her colleagues objects. Comets don't have magnetic fields. They're not geologically active. No dynamo, no magnetism. I know, she replies. That's the problem. Magnetic fields are generated by moving electric charges, currents flowing through conductive material. Planets like Earth have magnetic fields because molten iron in their cores circulates, driven by heat and rotation. This creates a dynamo effect. Small bodies like comets, asteroids, and moons are cold, solid, geologically dead. No circulation, no dynamo, no magnetism. There are exceptions. Certain iron-rich meteorites retain weak magnetic fields, fossilized remnants from when their parent bodies were molten billions of years ago. But those fields are faint, barely detectable even with sensitive instruments held centimeters away. The magnetic field required to produce the observed plasma streamers would need to be thousands of times stronger, strong enough to deflect solar wind, strong enough to organize ionized gas across thousands of kilometers. That kind of field requires an active dynamo, or something functionally equivalent. The physicist doesn't say the next thought out loud, but everyone on the call is thinking it. Electromagnets, superconducting coils, technology. No one wants to be the first to say it. December 18th. 24 hours before perihelion, closest approach to the Sun. The countdown is now measured in hours. Observatories around the world and in orbit prepare for the peak observing window. The object will reach maximum brightness, maximum temperature, maximum outgassing rate. Every instrument will be recording. Every telescope will be locked on. And then the Sun will eclipse it. From Earth's perspective, 3I Atlas will pass behind the Sun and vanish from view for 51 days. No observation will be possible. The Sun's glare is absolute. Even space telescopes, positioned away from Earth, Solar Orbiter Stereo, SOHO, will lose line of sight as the object swings around the far side of our star. 51 days of darkness. 51 days when the object will be invisible, untracked, unmonitored. 51 days when anything could happen. A mission planner at NASA's Jet Propulsion Laboratory reviews the orbital calculations one final time. She's confirming the predicted position of 3I Atlas when it emerges from behind the Sun in early February. The math is straightforward. The object is on a hyperbolic trajectory. Its path is determined by the Sun's gravity. Plug in the current position and velocity, run the equations, and you get the exit coordinates. The numbers are precise. When 3I Atlas reappears on February 8, 2026, it should be at a specific location, 14 degrees east of the Sun, moving outward at 47 kilometers per second, 190 million kilometers from Earth. She saves the prediction file. Then she adds a note in the mission log. Prediction assumes no non-gravitational forces during solar occultation. If object deviates, trajectory must be recalculated using post-emergence observations. Contingency plan recommended. It's a standard precaution. Comets sometimes surprise you. Outbursts happen. Jets activate. Orbits shift. But she's been working on comet missions for 18 years, and she's never felt the need to write contingency plan recommended before. She sends the file to her supervisor. No response comes. Late on December 18th, the last major scientific observation is conducted. The James Webb Space Telescope, positioned at the second Lagrange point 1.5 million kilometers from Earth, turns its enormous mirror toward 3I Atlas. JWST's infrared instruments can see through the coma, penetrating the glowing gas to image the nucleus directly. The observation lasts 6 hours. The resulting data is 4.7 terabytes, thousands of images across multiple infrared wavelengths compiled into a three-dimensional thermal map of the object's surface. The map reveals temperature variations, hot spots and cold spots distributed across the nucleus. This is expected. Solar heating is uneven. Surfaces facing the Sun heat up. Those in shadow cool down. But the hot spots don't align with the Sun-facing side. The warmest region, a patch roughly 400 meters across, is located on the object's dark side, the hemisphere currently in shadow. The temperature there is 520 degrees Celsius, 200 degrees hotter than the sunlit side. Heat doesn't flow backward. It doesn't accumulate in shadows, unless something is generating it internally. The JWST data is flagged for extended analysis. No preliminary results are released. No press briefing is scheduled. The observation is noted in the telescope's public activity log with a single line, Target 3I Atlas, status complete, remarks under review. Within hours, amateur astronomers download the log entry. The forums light up. What did they see? Why no statement? They always release preliminary findings, always. One user posts, they saw something they don't know how to explain. Another replies, or they saw something they do know how to explain, and that's worse. At 3:42 a.m. Universal Time on December 19, 2025, 3I Atlas reaches perihelion. Closest approach to the Sun. Distance, 76.3 million kilometers, roughly half the distance from the Sun to Earth, well inside the orbit of Venus. At this range, solar flux is intense. Temperatures on the sunlit surface exceed 600 degrees Celsius. Any remaining water ice sublimates violently. Volatile compounds, methane, carbon dioxide, ammonia, boil away. The outgassing rate should peak. The coma should explode outward in a brilliant display. Instruments detect the expected surge. The coma brightens by a factor of 4 over the span of 30 minutes. The tail, pushed by solar wind, extends to 12 million kilometers, longer than the diameter of the Sun. And then, quietly, the object begins its swing around our star. The Sun blocks the view. Earth-based telescopes lose sight. Space-based observatories track it for another 6 hours, watching it curve along its parabolic path, accelerating under the Sun's gravity like a stone whipped around on a string. At 11:18 a.m., the last telescope, ESA's solar orbiter, logs its final observation. The object is visible as a bright point of light, trailing a faint tail, receding into the Sun's glare. Then it's gone. Silence. The object is now traveling at 87 kilometers per second. Relative to the Sun, faster than any human-made spacecraft, fast enough to cross the distance from New York to Los Angeles in 45 seconds. It's moving outward, away from the Sun, back toward the cold outer reaches of the solar system. But for 51 days, no one will see it. For 51 days it will be alone with the Sun. And the math, cold, precise, indifferent, says that if anything changes during those 51 days, if the trajectory shifts by even a fraction of a degree, if the object maneuvers in the darkness where no one can see, we won't know until it reappears, and by then it might be too late. February passes in a fever of observation. Every major telescope, ground-based and orbital, remains locked on 3I Atlas. The object drifts outward beyond Mars, now 280 million kilometers from the Sun, moving at 52 kilometers per second. It should be fading, cooling, returning to the frozen silence of deep space. Instead, it continues to confound. The argon emissions persist, 2 kilograms per second, of noble gas venting into space from a surface that should be frozen solid. Argon doesn't sublimate at minus 130 degrees Celsius. It can't, unless it's stored under pressure, unless there's a reservoir, a tank, a chamber. Engineering, not geology. The thermal hotspot detected by JWST remains active. The temperature has dropped to 520 degrees Celsius, but that's still impossibly hot for an inert body at this distance from the Sun. The heat signature pulses with a 22-minute period, too regular for random outgassing, too persistent for dying thermal inertia. Something inside is generating power, cycling, operating. On March 2nd, radio telescopes detect a signal. It's faint, barely above background noise, but it's there, a narrowband emission at 327 megahertz. The frequency is significant. It's a protected band reserved for radio astronomy, rarely contaminated by terrestrial interference. The signal lasts 4 seconds. Then, silence. Over the next week, the signal repeats, not constantly, not predictably, but often enough to establish a pattern, 7 pulses, each 0.4 seconds long, separated by equal intervals. Then 90 seconds of silence. Then the pattern repeats, 7 pulses, always 7, always the same timing. Natural radio emissions from pulsars, magnetars, planetary lightning are either constant or chaotic. They don't produce patterns this precise, this structured, this deliberate. A researcher at the SETI Institute analyzes the signal's characteristics. Narrowband. Emissions require a transmitter. The 90-second interval suggests a programmed cycle. The 7-pulse structure implies intentionality, perhaps a counting sequence, perhaps a marker, perhaps something we don't yet understand. She writes in her report, "The signal exhibits properties inconsistent with known natural sources. If artificial origin is excluded a priori, no plausible explanation remains. The report circulates internally. It doesn't leak immediately, but word spreads through back channels. Scientists talk. Emails are forwarded. By March 5th, a journalist catches wind of the detection. The story breaks. Radio signal detected from interstellar object 3I Atlas. The public reaction is immediate. Forums explode. Social media trends. News networks run continuous coverage. The question everyone asks is the same. Is someone trying to communicate? NASA issues a statement on March 6th. Radio emissions detected near 3I Atlas are under investigation. Origin and nature remain uncertain. Premature conclusions should be avoided. The statement is careful, clinical. It says everything and nothing, but the absence of denial speaks louder than the words themselves. By mid-March, the scientific community is deeply fractured. Some researchers insist the signal must have a natural explanation. We simply haven't found it yet. Others argue that the accumulation of anomalies, chemical, thermal, kinematic, now electromagnetic, has crossed a threshold. Each anomaly alone could be explained away. Together they form a pattern that resists natural interpretation. A statistician at MIT runs a probability analysis. She compiles every documented anomaly: the nickel-to-iron ratio, the trajectory deviation, the argon release, the thermal hotspot, the radio signal. For each, she estimates the likelihood of natural occurrence based on existing scientific knowledge. Then she calculates the joint probability, the chance that all anomalies would occur together in a single object by pure coincidence. The result, 0.0004, 4 in 100,000. She doesn't publish the analysis, but she shares it with colleagues in a private email. The subject line, "How much evidence is enough?" One colleague responds, "Depends on what you're trying to prove." She replies, "I'm not trying to prove anything, I'm just following the numbers." No response comes. On March 18th, Avi Loeb publishes an essay in Scientific American, the title, "When the Improbable Becomes Unavoidable." He writes, "Science is built on evidence. When evidence contradicts our models, we refine the models. But when evidence contradicts all plausible models, when every natural explanation requires assuming multiple unlikely coincidences, then intellectual honesty demands we consider what we've been reluctant to consider." He continues, "The hypothesis that 3I Atlas is artificial is testable. It makes predictions. It can be falsified. Refusing to test it is not skepticism, it's avoidance." The essay is measured, rational, but the conclusion is unavoidable. We should be investigating the possibility that 3I Atlas is not natural, not as wild speculation, as rigorous hypothesis. The response is explosive. Some scientists publicly support Loeb's call for open investigation. Others denounce him as reckless. Loeb is giving legitimacy to pseudoscience, one prominent astronomer tweets. "We don't need evidence of alien probes, we need better models." But others are less certain. A planetary scientist at Caltech writes, "I've spent 20 years studying solar system bodies. I don't know what 3I Atlas is, and neither does anyone else. Pretending we do is dishonest." The debate escalates. It's no longer just about 3I Atlas. It's about epistemology, how we know what we know. It's about scientific methodology. It's about the boundaries between skepticism and denial. And beneath it all, unspoken but ever present, is fear. Fear of being wrong. Fear of being ridiculed. Fear of discovering something that changes everything. By late March, 3I Atlas is 320 million kilometers from the Sun, halfway between Mars and Jupiter. The radio signal continues its intermittent broadcasts. The thermal signature persists. The object drifts outward, neither accelerating nor decelerating, maintaining a parabolic trajectory that keeps it loosely bound to the Sun. It's not leaving. Not yet. It's waiting. Or so it seems. A mission analyst at ESA runs trajectory projections. If the object maintains its current velocity, it will exit the solar system entirely within 2 years. But if it maneuvers again, if it applies even a small amount of thrust, It could adjust its orbit, perhaps entering a more stable, periodic trajectory around the Sun. A holding pattern, a long-term presence. The analyst doesn't voice this speculation publicly, but she includes it in a classified briefing for ESA administrators. The briefing asks a question no one wants to answer. If the object remains in the solar system indefinitely, what do we do? No policy exists, no plan, no framework for managing the presence of an artificial object of unknown origin. The briefing is filed, marked for internal review. Nothing happens. On March 25th, an amateur astronomer in New Zealand captures an image of 3I Atlas through a backyard telescope. It's a grainy photo, just a faint dot against stars, but it's shared online and goes viral. The caption reads, "I'm looking at an object that might be proof we're not alone. And I'm just a guy in my backyard. This is the most important moment in human history, and most people are scrolling past it." The post is shared 100,000 times. A reply, upvoted thousands of times, reads, "Or it's just a weird rock. But yeah, probably aliens." Another, "If it is aliens, they picked a hell of a way to say hello." The tone is joking, ironic, but beneath the humor is something else. A quiet recognition that the world has changed, that the universe revealed something unexpected, that certainty has crumbled, and no one, scientist or skeptic, believer or cynic, knows what comes next. The object drifts, the signal pulses, the data accumulates, and humanity watches, waiting for an answer that may never come. Or worse, waiting for an answer that does. April arrives with no new revelations, no sudden disclosures, no clarifying breakthroughs. 3I Atlas continues outward, now 360 million kilometers from the Sun, deep in the asteroid belt's territory. The radio signal persists, 7 pulses, 90-second intervals, intermittent but regular. The thermal signature has faded to barely detectable levels. The argon emissions have stopped. The object is quieting, not dying, not fragmenting, just powering down, as if its work here is finished, as if it's entering a dormant phase, conserving energy for the long journey ahead, or the long wait. By mid-April, the initial frenzy of public attention begins to wane. News cycles move on. Other crises demand headlines. 3I Atlas becomes background noise, still monitored, still discussed in scientific circles, but no longer the center of global conversation. The world, it seems, has decided to live with uncertainty. Not everyone agrees this is wise. On April 10th, a group of scientists, ethicists, and policy experts convene a private conference in Geneva. The topic, Protocols for Contact with Non-Terrestrial Intelligence. The meeting is invitation only, no press, no public announcement. Participants include astronomers from NASA, ESA, and the European Southern Observatory. Also present, representatives from the United Nations Office for Outer Space Affairs, philosophers specializing in ethics and existential risk, and several government officials from spacefaring nations. The meeting lasts 2 days. Discussions are intense, sometimes heated. The central question is deceptively simple. If 3I Atlas is artificial, what should humanity do? No consensus emerges. Some argue for immediate attempts at communication, responding to the radio signal, broadcasting messages toward the object, attempting to establish dialogue. Others urge extreme caution, pointing out that we know nothing about the object's origin, purpose, or intentions. First contact should not be improvised, one participant argues. We need protocols, international agreements, a unified human response. Another counters, we don't have time for bureaucracy. If the object is listening, if it's waiting for a response, delay could be interpreted as hostility, or indifference or fear. A third voice interjects, or maybe it doesn't care what we do. Maybe we're irrelevant to its purpose. That possibility, that humanity might be witnessing something profound, but ultimately peripheral to our existence, is perhaps the most unsettling of all. The meeting concludes with a draft framework for potential engagement scenarios, but no formal recommendations are issued. The framework is filed with the UN. It will be reviewed. Eventually, bureaucracy moves slowly. The universe does not. Meanwhile, independent researchers continue analyzing the radio signal. A team at Caltech applies advanced signal processing techniques, searching for hidden structure beneath the 7-pulse pattern. They find nothing, no modulation, no embedded data, just pulses. A linguist at MIT examines the pattern from a communication theory perspective. If this is a message, she says, it's either extremely simple or extremely sophisticated. Simple messages are easy to decode, counting sequences, prime numbers, basic mathematics. Sophisticated messages are impossible to decode without context. We don't know which this is. She pauses. Or it's not a message at all. It could be leakage, unintentional radiation from internal systems, a byproduct, not a broadcast. That interpretation gains traction. If the object is artificial, its radio emissions might not be intended for us. They might just be noise. The electromagnetic equivalent of engine hum, which raises a different question. If it's not trying to communicate, what is it doing? No one knows, and the object isn't offering clues. By late April, 3I Atlas is 400 million kilometers from the Sun. It's now farther from Earth than Earth is from the Sun. A psychological threshold that feels significant, even though distance in space is relative. The trajectory projections are updated. If the object maintains its current velocity and direction, it will exit the solar system entirely by mid-2028, 2.5 years from now. Then it will vanish into interstellar space, becoming once again a traveler in the void, invisible and unreachable, unless it changes course. That possibility haunts mission planners. The object maneuvered once during the 51 days behind the Sun. It could maneuver again, and if it does, all predictions become meaningless. A contingency plan is drafted at NASA. The plan outlines how tracking assets would respond if the object suddenly alters trajectory, which telescopes would prioritize observation, which data would be collected, how information would be disseminated. The plan is classified for official use only. It's not made public, but its existence is telling. Someone, somewhere, is preparing for the possibility that 3I Atlas is not done surprising us. On April 22nd, Earth Day, an environmental group organizes a global event. Watch the skies. The idea is simple. Encourage people to observe 3I Atlas through telescopes, binoculars, even just with naked eyes if conditions are right. The object is faint but visible to dedicated amateurs with decent equipment. Thousands participate. Images flood social media. Most show faint dots against star fields. Some show nothing, clouds, light pollution, or simple misidentification. But the act of looking, of collectively turning human attention toward a single point in space, feels significant. A philosopher writes in an op-ed, "We're watching because we don't know what else to do. The object has given us a mystery but no answers. So we watch, we wait. We hope that observation alone might bring understanding." She continues, "But maybe the real revelation isn't about the object. Maybe it's about us, about how we respond to the unknown, with fear, with curiosity, with denial." The essay is shared widely. It resonates, not because it provides answers, but because it articulates what millions are feeling. We are witnesses to something unprecedented, and we don't know what it means. On May 1st, the radio signal changes. Not the pattern, still 7 pulses, still 90-second intervals, but the frequency shifts. Instead of 327 megahertz, the signal now broadcasts at 428 megahertz, higher frequency. Same structure. Radio telescopes detect the change within hours. Confirmation comes from multiple observatories. The shift is real. A radio astronomer at Jodrell Bank in the UK analyzes the new frequency. 428 megahertz is still within protected radio astronomy bands, she notes. It's not random. Both frequencies, 327 and 428, are used for scientific observation, deliberately kept clear of commercial interference. She pauses. If the object is choosing these frequencies deliberately, it suggests awareness, knowledge of which bands we monitor. The implication is unsettling. If the object knows which frequencies humans use for astronomy, then it knows we're here, it knows we're listening, and it's choosing to broadcast on frequencies we can detect. Or, less ominously but equally intriguing, the frequencies are simply where natural physical processes happen to emit, and the object is leveraging those processes for its own purposes. No way to know, not yet. The signal continues. 7 pulses. Silence. Repeat. By mid-May, 3I Atlas is 450 million kilometers from the Sun, well beyond Mars, approaching the outer edge of the asteroid belt. The object is now so distant that even large telescopes struggle to resolve surface features. It's becoming a point of light again, anonymous, distant, receding. The public's attention has largely moved on. News coverage is sporadic. Social media buzz has faded. The object has joined the background hum of ongoing mysteries, acknowledged, unresolved, but no longer urgent. Scientists, however, remain vigilant. On May 20th, a young astrophysicist at Oxford publishes a paper titled The Paradox of 3I Atlas, Evidence, Explanation, and Epistemology. The paper doesn't claim to solve the mystery. Instead, it examines how scientific communities respond to anomalies that resist categorization. She writes, "When confronted with data that contradicts all existing models, science faces a choice: expand the models or challenge the assumptions underlying them. The history of science shows that both paths are sometimes necessary, but which path we choose depends not just on evidence, but on what we're willing to consider possible." She continues, 3I Atlas forces us to confront a question we've long avoided. Are we alone? But it forces us to confront it without providing a definitive answer. We're left in epistemic limbo, enough evidence to question, but not enough to conclude. This is perhaps the object's most profound effect, not revelation, but sustained uncertainty. The paper is widely discussed. It becomes required reading in philosophy of science courses. It's cited in editorials, podcasts, and late-night debates. Because it captures something essential, we may never know. The object might leave the solar system still shrouded in mystery. Years from now, historians might look back on 3I Atlas as the moment humanity glimpsed something extraordinary, but only glimpsed. A shadow, a whisper, a signal in the noise, not proof, not contact, just something. And maybe that's enough, or maybe it's unbearable. On June 5th, 2026, 3I Atlas crosses 500 million kilometers from the Sun. The radio signal weakens but continues. The object is now moving through the space where Jupiter's orbit lies, though Jupiter itself is currently on the far side of the Sun, nowhere near the object's path. A final major observation campaign is organized. Hubble, JWST, the VLT, and dozens of other telescopes conduct coordinated observations over a 48-hour window. The goal? Capture as much data as possible before the object becomes too faint to study in detail. The observations are successful. Spectra, thermal maps, high-resolution images, everything is recorded. The data will take months to fully analyze, but preliminary findings show nothing new. The object is inert, dark, silent, except for the faint, intermittent radio pulses. It's returning to the state it was in when it arrived, a cold, enigmatic traveler, indistinguishable from a comet except for the trail of anomalies it leaves in the data. By late June, media coverage has all but ceased. A few science journalists continue writing updates, but the audience has dwindled. The mystery of 3I Atlas has become part of the ambient noise of unsolved questions, alongside dark matter, consciousness, and the origin of life. Important, fascinating, but not urgent. Life goes on. On July 15th, a research group at Harvard publishes a comprehensive review paper, 3I Atlas, a summary of observations and implications. The paper is 87 pages long, meticulously documented, peer-reviewed by a dozen experts. The conclusion is careful. 3I Atlas exhibits properties inconsistent with known natural cometary behavior. While several hypotheses have been proposed, none fully accounts for the observed phenomena. Further observation and theoretical work are required. The possibility of artificial origin, while speculative, cannot be dismissed without additional evidence. It's the closest any major scientific publication has come to stating the obvious. We don't know what it is. It might be natural, it might not. And we might never know. The paper is downloaded 200,000 times in the first week. It's cited in follow-up studies, mentioned in textbooks, referenced in policy discussions. It becomes the definitive summary of humanity's encounter with 3I Atlas. But it doesn't provide closure, because closure isn't available. By August 2026, 3I Atlas is over 600 million kilometers from the Sun, well beyond the asteroid belt, drifting into the vast emptiness between Mars and Jupiter. The radio signal is now barely detectable. The object is a faint dot even in the world's largest telescopes. It will take 2 more years for it to exit the solar system entirely. 2 more years of slow drift into the dark. Astronomers will continue monitoring. Amateur observers will keep watch. The data will continue accumulating, analyzed by researchers who hope that one final piece, one overlooked detail, might unlock the mystery. But deep down, most accept the truth. 3I Atlas will leave as it arrived. Unknown, unexplained. A question without an answer. A signal in the silence. Epilogue. The Waiting Game. September 7th, 2027. Exactly. 2 years since 3I Atlas was first detected. The object is now 1.2 billion kilometers from the Sun, far beyond Jupiter's orbit, in the cold outer reaches of the solar system. It's invisible to all but the most powerful telescopes. The radio signal ceased months ago. The thermal signature is gone. 3I Atlas is dark, silent, inert, but it's still here. Trajectory calculations show the object will cross the heliopause, the boundary where the Sun's influence gives way to interstellar space, sometime in late 2028. Then it will be gone, truly gone, unreachable by any human-made spacecraft, invisible to any telescope. A ghost fading into the cosmic background. A few dozen researchers worldwide still monitor its position. Updates are logged, data is archived, papers are written, though fewer each month. The mystery hasn't been solved, it's simply faded. But sometimes, late at night, an astronomer in Chile or Hawaii or Australia will point a telescope toward the coordinates where 3I Atlas drifts. They'll capture an image, a faint smudge of reflected sunlight against the stars, and they'll wonder. Was it natural? A comet with properties we've never encountered before, a cosmic fluke that challenged our models but ultimately fit within the bounds of physics? Or was it something else? A probe, a sentinel, a messenger from a civilization that looked at our sun, our system, our little blue world, and decided to visit. Not to conquer, not to communicate, just to look, to observe, to leave. We may never know. Decades from now, historians might look back on 3I Atlas as an inflection point, the moment humanity first confronted the possibility that we are not alone. Or they might see it as a cautionary tale about overinterpretation, about seeing patterns in noise. Both narratives are plausible, neither is provable, and perhaps that's the real legacy of 3I Atlas. Not an answer, but a question that will echo through the decades, through the centuries, through every future moment when humanity looks up at the night sky and wonders, what else is out there? Are they watching? Have they already been here? On October 10th, 2027, a final major article is published in Nature. The title, 3I Atlas and the Limits of Knowledge. The article is philosophical as much as scientific. It argues that some mysteries may be fundamentally unsolvable, not because we lack intelligence or technology, but because the universe is under no obligation to provide answers we can understand. We wanted certainty, the article concludes. We got ambiguity. We wanted revelation. We got a whisper. And maybe that's the most honest thing the universe has ever told us, that we are small, that we are limited, and that the cosmos is full of things we will never fully comprehend. But we looked, we tried. We followed the evidence as far as it would take us. And that, in itself, is worth something. The article is shared widely. It resonates not just with scientists, but with anyone who followed the story, with anyone who looked up and wondered. Because 3i Atlas didn't give us answers, but it gave us something else. A reminder that the universe is stranger than we imagined. A reminder that we are not the center of everything. A reminder that mystery still exists. And maybe, just maybe, a reminder that we are not alone, even if we can't prove it, even if we'll never know for sure. Final scene, December 19th, 2028. 3 years to the day since 3i Atlas reached perihelion. A radio telescope in New Mexico detects a faint signal, 327 megahertz, the same frequency as before. 7 pulses, 0.4-second intervals, 90 seconds of silence. Then nothing. The signal is logged, cross-checked, verified. It came from the direction of 3i Atlas, now 2.1 billion kilometers away, beyond the orbit of Uranus on the edge of leaving forever. One final transmission, one last pulse, and then silence. The object crosses into interstellar space 3 months later. It's tracked as far as instruments allow, then it fades, vanishes, becomes one more invisible traveler among trillions. Somewhere out there, in the dark between stars, 3i Atlas drifts, silent, alone, unknown, carrying with it the question humanity could never answer. What were you? And perhaps, if the universe is listening, carrying one more question. Will you come back? The sky offers no reply. Only stars. Only silence. Only the vast, indifferent beauty of a cosmos that holds its secrets close. And humanity, small, curious, relentless, keeps watching, keeps wondering, keeps hoping, because that's what we do. We look up, we ask why, and we wait.